The universe contains roughly 2 trillion galaxies. Hundreds of billions of stars burn inside each one. There are more stars in the observable universe than grains of sand on every beach on Earth. And yet, when you step outside at night, you see darkness. Black, empty, endless darkness between tiny points of light. For most of human history, no one thought twice about that. The dark sky was just what night looked like. But in the early 1800s, astronomers realized something deeply wrong with that picture. If the universe is full of stars, the sky should not be dark. Every direction you look should end at a star. The entire sky should glow as bright as the surface of a sun. It does not, and the reason is horrifying. Before we go any further, if you find this kind of deep exploration interesting, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Now, are you comfortable? Let's begin. Step outside tonight. Find a place where the city lights thin out, where the glow of street lamps and phone screens cannot reach you. Let your eyes adjust. Give them 10 minutes, maybe 15, and then look up. What you see is something so familiar that you have probably never questioned it. Stars, scattered across a black canvas. Thousands of them, some bright, some faint, most barely visible, all of them separated by stretches of darkness so total that no light exists there at all. The sky between the stars is black. Not dark blue, not dim. Black. You have seen this your entire life. Everyone who has ever lived has seen it. The dark night sky is one of the oldest and most universal human experiences. Shepherds in ancient Mesopotamia saw it. Sailors crossing the Pacific saw it. Every child who has ever pointed at a star and asked what it is saw it. The blackness between the stars seems like the most obvious thing in the universe. The sky is dark at night because the star we orbit has set and the stars are far away. What else would it be? That is the assumption, and for thousands of years nobody challenged it. The dark sky was simply what existed after sunset. Background, silence, nothing worth explaining. Then, starting in the 1600s, a few astronomers looked at that darkness more carefully, and what they found was not nothing. What they found was a contradiction so deep, so unsettling, that it would take centuries to resolve, and the resolution would reveal something about the universe that most people still do not fully grasp. The night sky is not dark because space is empty. The night sky is dark because the universe has limits. And those limits are written in the blackness itself. To understand why the darkness is strange, you have to start with what astronomers believed about the universe for most of recorded history. For centuries, the dominant assumption was that the universe is infinite. It stretches forever in every direction, populated with stars scattered more or less evenly through all of space. There is no edge. There is no boundary. Stars go on and on without end. If that assumption is true, something alarming follows. Imagine standing in a forest, not a small forest, an infinite forest. Trees in every direction, stretching endlessly no matter how far you walk. Now look in any direction. What do you see? A tree. Maybe it is close, maybe it is far. But if the forest is truly infinite and the trees are spread throughout it, then no matter which direction you look, your line of sight will eventually hit a trunk. There is no gap. There is no direction where you could stare forever and see open sky. The trees fill every sight line. Now replace the trees with stars. If the universe is infinite and filled uniformly with stars, then every direction you look should eventually end at the surface of a star. It might be close, or it might be unimaginably far away. But somewhere along that line of sight, a star is burning, and light from that star is traveling toward you. Add up all those lines of sight. Every direction, every angle, every tiny patch of sky, each one terminates at a star. The result is a sky that does not have dark spots at all. The entire dome above you, from horizon to horizon, should glow with the combined light of every star along every possible sight line. The brightness should be comparable to the surface of a star, not a few twinkling points, a continuous wall of light. The night sky should look like the inside of a furnace. It does not. And that fact, once you truly understand it, becomes one of the most important clues in the history of science. The first person known to have recognized this problem was Johannes Kepler. In 1610, Kepler was thinking about the arrangement of stars in the heavens. He understood that if the universe were infinite and filled with stars, the sky should not be dark. He used this reasoning in reverse. The dark sky, he argued, was evidence that the universe of stars does not go on forever. There must be an edge, a boundary, an end to the starfield. Beyond it, emptiness. Kepler did not have the tools to test this idea. He did not know how far the stars extended, or what lay beyond them. But he recognized the logical connection between darkness and finitude. The dark sky told him something about the shape of the cosmos. More than a century later, the English astronomer Edmund Halley revisited the question. Halley considered the possibility that distant starlight might simply be too faint to see. Perhaps the combined glow of extremely remote stars would fade below the threshold of human perception. But the mathematics did not support this escape. In an infinite universe, the number of stars at any given distance increases with the square of that distance, which exactly compensates for the dimming of each individual star by the inverse square law. The contributions add up. The faint distant glow does not vanish. It accumulates. Shell after shell of stars, each contributing its share, until the total reaches the brightness of a stellar surface. Here is a way to feel this intuitively. Imagine concentric shells of space surrounding the Earth, one after the other, each slightly larger than the last, each containing stars. The nearest shell contains a handful of stars that are bright because they are close. The next shell is farther away. Each individual star in that shell is dimmer, but the shell is bigger, so it contains more stars. Those two effects cancel each other perfectly. The total light from each shell is the same, regardless of how far away it is. A shell 1 billion light years out contributes the same total brightness as a shell 1,000 light years out. In an infinite universe with infinite shells, the total brightness is infinite. Take a moment with that, because the intuition fights it. Your instinct says that a star 10 billion light years away must contribute less than a star 10 light years away. And individually it does. One distant star is incomparably dimmer than one nearby star. The brightness of a single point source drops with the square of the distance. A star twice as far away is 4 times dimmer. A star 10 times as far away is 100 times dimmer. A star 1,000,000 times as far away is 1,000,000,000,000 times dimmer. That is the inverse square law, and it is real. But the number of stars is not fixed. In a uniform universe, the number of stars in a given shell increases with the square of the distance, because the surface area of the shell increases with the square of its radius. A shell twice as far away has 4 times the surface area, and therefore contains 4 times as many stars. A shell 10 times as far away has 100 times as many. A shell 1,000,000 times as far away has 1,000,000,000,000 times as many. The dimming and the multiplication cancel each other perfectly. Every shell, regardless of distance, delivers the same total amount of light. This is not a rough approximation, it is exact. It falls directly out of the geometry. Now add up the shells. In an infinite universe, there are infinite shells. Each one contributes the same finite amount of brightness. An infinite number of identical finite contributions produces an infinite total. The math is not complicated. It is not ambiguous. It is relentless. In an infinite, eternal, uniformly filled universe, the brightness of the sky is infinite. In practice, the sky would not literally reach infinite brightness, because at some point the nearby stars would block the view of the ones behind them, the way the front row of a crowd blocks the back rows. The brightness would plateau at a level comparable to the average surface brightness of a star, but that plateau is itself blindingly bright. The surface of our star burns at roughly 10,000 degrees Fahrenheit. Imagine that temperature radiating from every point in the sky simultaneously, above you, below the horizon, from every direction, an oven with no walls and no way out. That is what the math demands, and the sky refuses to comply. This is why the paradox has teeth. It is not a quirky intellectual puzzle. It is a flat contradiction between a seemingly reasonable set of assumptions and the plainest observation available to any human being who steps outside after dark. Something in the assumptions is catastrophically wrong, and the dark sky is the proof. The sky should be on fire, every direction, all the time. Halley could not resolve the problem. He acknowledged its strangeness and moved on to other work. Then, in 1823, a German astronomer named Heinrich Wilhelm Olbers published a paper that would permanently attach his name to the question. Olbers laid out the logic with precision. He accepted the prevailing assumption of an infinite, static, uniformly populated universe. He followed the geometry to its inescapable conclusion. The sky should be ablaze. And then he proposed a solution. Olbers suggested that interstellar dust and gas might absorb the light from distant stars. If enough material floated between the stars, it could block the light before it reached our eyes. The distant furnace would be hidden behind a curtain of particles. The sky would appear dark, not because the light was absent, but because it was absorbed before arrival. It was an elegant idea. It was also wrong. The reason it was wrong would not be fully articulated until later in the 19th century, when the Scottish physicist William Thomson, known as Lord Kelvin, applied the laws of thermodynamics to the problem. And the way he dismantled the dust explanation is one of the cleanest pieces of physical reasoning in the history of cosmology. Start with a single grain of interstellar dust. It is extraordinarily small, perhaps a fraction of a micrometer across, made of silicates or carbon compounds or ice. It floats in the void between stars, cold and dark. A photon of starlight arrives and strikes the grain. The grain absorbs the photon. At this point, the light is gone. It has been removed from the sight line, one fewer photon traveling towards a distant observer. The dust did its job. The sky is slightly darker. But the photon's energy did not vanish. Energy cannot be created or destroyed. That is the first law of thermodynamics, and it is absolute. The energy of the absorbed photon has been transferred to the grain. The grain is now very slightly warmer than it was before. Its atoms vibrate a little faster. Its temperature has increased by an almost immeasurably small amount. Now another photon arrives, and another, and another. Over thousands of years, millions of years, the grain absorbs photon after photon, and its temperature climbs. As it warms, the grain begins to do something unavoidable. It begins to radiate. Every object with a temperature above absolute zero emits electromagnetic radiation. That is a fundamental law of physics. A warm object in a cold environment radiates energy. The hotter it gets, the more it radiates. The grain, heated by the starlight it has been absorbing, starts emitting infrared photons of its own, sending them outward in all directions. At first, the grain absorbs more energy than it radiates. It continues to warm, but as its temperature rises, its radiation output increases. Eventually, the grain reaches a temperature where it radiates exactly as much energy per second as it absorbs. At that point, it is in thermal equilibrium with its surroundings. It has become a tiny lamp, glowing steadily in the infrared, powered by the very starlight it was supposed to be hiding. Now multiply that single grain by every grain of dust in the universe. In an infinite cosmos filled with infinite starlight, every grain of dust eventually reaches thermal equilibrium. Every grain becomes a radiator. The dust does not hide the light, it converts it. Visible photons go in. Infrared photons come out. The total energy is conserved. The sky is still flooded with radiation, just at a different wavelength. And in an eternal universe with infinite time, even that wavelength distinction disappears, because the dust and the starlight and the radiation field all reach a common equilibrium temperature, and the entire contents of space glow uniformly at the temperature of the average stellar surface. The curtain becomes a lantern, the shield becomes a mirror. There is no material in the universe that can absorb infinite energy without eventually giving it back. Kelvin's argument was devastating in its simplicity. That is the thermodynamic verdict, and there is no way around it. No material in the universe, no grain of silicate, no cloud of carbon, no curtain of ice crystals drifting between the stars, can absorb energy without eventually returning it. The process might take thousands of years or millions or billions. The re-radiated energy might emerge at a different wavelength, shifted from visible light into infrared or beyond, but it emerges. The budget always balances. The total energy in the radiation field is determined by the total luminosity of the stars, and no intervening material changes that budget, no matter how thick, no matter how opaque, no matter how widely distributed. Every proposed curtain becomes a lamp. Every shield becomes a mirror. Every material barrier that absorbs starlight will, given sufficient time, glow with the same intensity it was supposed to block. The dust explanation does not merely weaken under scrutiny, it collapses entirely. And with it goes the last easy answer. This is the heart of what became known as Olbers' paradox, though the name is somewhat misleading. Olbers did not discover the paradox. Kepler noticed it 2 centuries earlier, and Olbers' proposed solution, the dust hypothesis, turned out to be the wrong answer. But his paper brought the problem to wide attention among the European scientific community, and his name stuck. The word paradox matters here. It does not mean mystery. It does not mean question. It means contradiction. The assumptions say the sky should be bright. Observation says it is dark. Both cannot be true at the same time. Something in the assumptions must be wrong, and whichever assumption breaks will reveal something fundamental about the nature of the universe itself. For decades after Olbers, the problem sat unresolved. Astronomers acknowledged it, discussed it at conferences, debated it in letters, and moved on to other questions. The night sky remained dark. The paradox remained open. The universe continued to refuse to match the prediction. Then, in 1848, an answer arrived from the most unlikely source imaginable. Edgar Allan Poe was not an astronomer. He was not a physicist. He was not a mathematician. He was a writer, a poet, a man known for Gothic horror, for tales of madness and death, for ravens and buried hearts, and the slow creeping terror of the unknown. He spent his career mapping the contours of human dread. He was also, it turns out, someone who thought very deeply about the cosmos. By 1848, Poe was near the end of his life, and he seemed to know it. His wife Virginia had died of tuberculosis the year before. He was drinking heavily, writing sporadically, and struggling to maintain the literary reputation he had built over 2 decades. He had invented the modern detective story with his tales of Auguste Dupin. He had written some of the most celebrated poems in the English language. He had terrified a generation of readers with stories that probe the edges of sanity, death, and the unknowable. And now, in the final stretch of a life marked by loss and instability, he turned his attention to the largest question he could imagine. What is the universe? The ambition of the project was staggering, and Poe seemed aware that it would invite ridicule. He wrote in the preface that he wished the work to be judged as a poem, even though it dealt with scientific and mathematical ideas. He described it as offering a truth that could be felt through intuition and beauty, rather than proved through experiment alone. He knew the scientific establishment would not take him seriously. He was not a trained physicist. He had no telescope. He had no data. What he had was a ruthless logical mind, a deep familiarity with the astronomical literature of his day, and the same instinct for hidden patterns that made his detective fiction so effective. Poe delivered the initial version of the work as a lecture at the Society Library of New York in February of 1848. The audience was small. Reviews were mixed. Some listeners were fascinated, others were baffled. The published version, which appeared later that year under the title Eureka, a prose poem, sold poorly. The scientific community largely ignored it. Poe died the following year at the age of 40, under circumstances that remain disputed to this day, and Eureka faded from public attention. It would take more than a century for anyone to recognize what Poe had done. The irony is almost too perfect. The man who built his career on darkness, who wrote about premature burial, about plague, about the terror of being sealed inside spaces from which there is no escape, looked at the actual darkness of the night sky and saw not a backdrop but a clue. He treated the dark sky the way Dupin would treat a crime scene, examining the evidence, discarding the obvious explanations, and arriving at the truth through deduction alone. The work that emerged from that February lecture, revised and expanded for publication later that same year, was unlike anything else in his catalogue. He called it Eureka, a prose poem. It was an attempt, ambitious to the point of audacity, to describe the origin and structure of the entire universe using logic, intuition, and the scientific knowledge available to him. Poe delivered the initial version as a lecture at the Society Library of New York in February of that year, then revised and expanded it for publication. Eureka is a strange and brilliant document. It mixes metaphysics with observation, poetry with physics, bold speculation with startling insight. Much of it was dismissed by the scientific establishment of the time. Poe himself seemed aware that his work would not be taken seriously during his lifetime. He dedicated it to the great naturalist Alexander von Humboldt and described it as a work that should be judged only after his death. Among the many ideas in Eureka, one passage stands out like a signal fire across 2 centuries. Poe considered the question of the dark night sky and arrived at an answer that was, for his era, breathtakingly original. He reasoned that if stars extended endlessly in all directions, then every point in the sky should show the light of a star. The background should glow uniformly. Since it does not, he proposed an explanation that no astronomer of his generation had articulated. The light from the most distant regions of the universe has simply not had time to reach us. Poe understood that light travels at a finite speed. That much was established science by 1848. And he also intuited something that the cosmology of his day had no theoretical framework to support. That the universe might not be infinitely old. If the cosmos had a beginning, then the light from stars beyond a certain distance would still be in transit. It would be on its way, crossing the void, but it would not have arrived. There would be a horizon, a boundary not in space but in time, beyond which no information had yet reached us. And beyond that horizon, the sky would be dark. Poe wrote that the only way to explain the dark gaps that telescopes find in innumerable directions would be by supposing the distance of the invisible background so immense that no ray from it has yet been able to reach us at all. Consider the date, 1848. Charles Darwin had not yet published On the Origin of Species. The American Civil War was more than a decade away. The concept of galaxies beyond the Milky Way would not be established for another 75 years. The Big Bang Theory did not exist, even as a hypothesis, and yet Poe, working from pure deduction, arrived at the essential insight that would later become a cornerstone of modern cosmology. The universe is not infinitely old. Light takes time to travel. And the darkness between stars is not evidence of emptiness. It is evidence of distance and time so vast that light has not yet crossed it. The physicist Edward Harrison, who wrote the definitive 20th century analysis of the dark night sky problem, credited Poe with providing the first qualitative solution to the paradox. Not a mathematical proof, not a model that could be tested with instruments, but a logical insight so sharp and so correct that it anticipated the structure of the modern answer by more than a century. There is something haunting about this. The man who spent his career writing about darkness, about the terror of what lurks beyond the edge of perception, about the thin membrane between what we know and what we cannot see, turned his gaze to the actual sky and found the same principle written there. The universe itself hides things, not with walls, not with curtains, not with dust, with the simple fact that light cannot travel infinitely fast through a cosmos that has not existed forever. The darkness is not a void, it is a boundary, and beyond it, light is still on its way. Poe was right, but his answer was incomplete. He identified one half of the solution. The finite age of the universe limits how far light has had time to travel, and that limit creates a dark horizon beyond which we cannot see. But there is a second half, equally important, equally unsettling, that Poe could not have known about. Because the universe is not just old, it is not just vast. It is not simply sitting there while light crawls across it at 186,000 miles per second, slowly filling in the dark patches. The universe is doing something far stranger. It is expanding. And the expansion changes everything about what the darkness means, about what light can reach us, and about what is being hidden from us right now as you listen to this. Because the expansion of space does something to light that no amount of distance alone can do. It does not just delay the light, it transforms it, it stretches it, and in many cases, it erases it entirely from the range of anything human eyes could ever detect. That story, the story of what expansion does to the light of the cosmos, and why the sky is not just dark but destined to become darker, begins with a discovery made in 1929 that turned the entire picture of the universe inside out. Before we get to the discovery that turned the universe inside out, we need to understand something more fundamental, something about light itself. Because even without the revolution that came in 1929, the darkness of the night sky already has an explanation that cuts straight through the paradox. And that explanation begins with a single fact that humans have known for more than 3 centuries. Light is fast, but it is not instant. When you flip a switch in a room, the light appears to fill the space immediately. There is no visible delay, no moment of waiting. That is because light crosses a room in roughly a billionth of a second. At human scales, the speed of light is so enormous that it might as well be infinite, but it is not infinite. And at cosmic scales, that distinction changes everything. Light travels at approximately 186,000 miles per second. In a vacuum, nothing moves faster. That speed was first measured with reasonable accuracy in 1676 by the Danish astronomer Ole Romer, who noticed that the timing of eclipses of Jupiter's moon, Io, shifted depending on how far Earth was from Jupiter in its orbit. When Earth was closer, the eclipses arrived slightly early. When Earth was farther, they arrived slightly late. Romer realized the difference was caused by the extra distance the light had to travel. Light was not instantaneous, it had a speed. And that speed, while staggering, was finite. That finitude has a consequence that reaches across the entire universe. When you look at the moon, you are not seeing it as it is right now. You are seeing it as it was 1.3 seconds ago, because that is how long the light took to cross the distance between you. When you look at our star during the day, you are seeing it as it was roughly 8 minutes ago. If it vanished at this very moment, you would not know for another 8 minutes, because the last photons it released would still be in transit, crossing the 93 million miles of space between there and here. Now, stretch that principle further. The nearest star beyond our own system, Proxima Centauri, is approximately 4.2 light years away. Its light takes more than 4 years to arrive. When you see it in the southern sky, you're looking at a star as it existed more than 4 years in the past. The bright star Sirius is about 8.6 light years away. The light you see left Sirius before some of the children born today were conceived. Go further still. The Andromeda galaxy, the nearest large galaxy to our own, is roughly 2.5 million light years away. When its light enters a telescope tonight, that light has been traveling since the dawn of the genus Homo, when our earliest ancestors were chipping crude stone tools from river cobbles on the African plains. You are not seeing a galaxy. You are seeing a ghost image, a portrait that predates every civilization in recorded human history. Keep going further. The center of our own galaxy, the dense core of the Milky Way, is roughly 26,000 light years away. The light arriving from it tonight left before the last ice age reached its peak. before humans painted bison and horses on the walls of the caves at Lascaux, before agriculture, before writing, before every civilization that has ever existed on this planet rose and fell. When that light began its journey, modern humans were hunting mammoths on frozen plains. The entire history of settled human life fits inside the travel time of a beam of light, from the center of our own galaxy. Now look beyond the Milky Way entirely. The Virgo cluster, a massive collection of more than 1,000 galaxies, lies roughly 54 million light-years away. Light arriving from it tonight departed when dinosaurs had been extinct for only 12 million years. The continents were still rearranging themselves after the asteroid impact. Early primates were just beginning to diversify in the forest of a recovering Earth. That is how far back you were looking when you point a telescope at the nearest large galaxy cluster. Go further still. The Coma cluster, one of the richest galaxy clusters known, lies roughly 320 million light-years away. Its light left during the Carboniferous period, when the first great forests of fern and scale trees were building the coal deposits that would one day fuel the Industrial Revolution. Giant arthropods and amphibians dominated the land. The first true reptiles had not yet appeared. The light from the Coma cluster has been traveling since before any reptile, any mammal, any bird, any flower existed on Earth. Each step outward in distance is a step backward in time. The sky is not a single image, it is a series of concentric shells, each one showing the universe at a different age, each one older than the last. The stars you see with the naked eye show you the recent past. The nearest galaxies show you millions of years ago. The great clusters show you hundreds of millions of years ago. And the most distant objects accessible to modern telescopes show you the universe as it was more than 13 billion years ago, when the cosmos itself was barely recognizable. This is the insight that transforms the night sky from a picture into a history. Every object you see in space, you see as it was in the past. The farther away it is, the deeper into history you are looking. A galaxy 1 billion light-years away appears as it was 1 billion years ago. A galaxy 10 billion light-years away appears as it was 10 billion years ago. The sky is not a snapshot. It is a stack of moments, layered one behind the other, each one older than the last, reaching backward in time towards the beginning of everything. Every telescope ever built is a time machine, not a metaphorical one, a literal one. It does not transport you to the past, but it shows you the past, carried to your eyes on beams of light that left their sources years or millennia or billions of years ago and have been crossing the void ever since. Now apply this to the paradox. The universe is approximately 13.8 billion years old. That number comes from multiple independent lines of evidence. The rate at which galaxies move apart, the temperature and structure of the oldest light in the cosmos, the abundances of the lightest elements forged in the first minutes after the Big Bang, and the ages of the oldest known stars. These measurements agree. The universe had a beginning, and that beginning occurred roughly 13.8 billion years ago. This single fact demolishes one of the key assumptions behind the paradox. The paradox assumed the universe is eternal, that stars have been shining forever, that light has had infinite time to travel, and that every sight line has had enough time to be filled with stellar light from every distance. If the universe is 13.8 billion years old, none of that is true. Light has had only 13.8 billion years to travel. That means there is a maximum distance from which light could have reached us since the beginning. Beyond that distance, The photons are still in transit. They have been traveling since the moment they were emitted, crossing space at 186,000 miles per second, and they have not arrived yet. They are out there right now, moving through the void, but they have not reached Earth. They might not reach Earth for billions of years, or, as will become clear shortly, they might never arrive at all. This creates a boundary, not a wall, not a physical barrier, a horizon. It is the edge of what light has had time to show us. Astronomers call it the observable universe, and its radius, accounting for the fact that space has been expanding while the light travelled, is approximately 46 billion light years in every direction. Everything inside that sphere is visible to us in principle. Everything outside it is not. Not because it does not exist, but because the light from those regions has not had enough time to make the journey. The observable universe is not the whole universe, it is our window, and the window has a size determined by the age of the cosmos and the speed of light. Beyond the window, the universe almost certainly continues. There may be galaxies out there, stars burning, planets orbiting, perhaps even other observers staring into their own dark skies and wondering the same things we wonder. But their light is beyond our horizon. We cannot see them. We have no information from them. For all practical purposes, they do not exist in our picture of the cosmos. This is the first reason the night sky is dark. Not every line of sight ends at a star, because there has not been enough time for the light from every star to reach us. The dark patches are not empty. They are full of stars whose light is still on the way, or whose light was emitted from beyond the horizon, or whose light was released so long ago and from so far away that it has been stretched and weakened to the point where human eyes cannot detect it. Poe was right. The darkness is a signature of finitude. The universe has an age, and that age draws a circle around us. Inside the circle, there's light. Outside the circle, there is silence. Not because nothing exists there, because time has not carried the message far enough, but the finite age of the universe is only part of the answer. The paradox also assumed something else that turns out to be wrong. It assumed that stars are eternal, that they burn forever, filling space with an endless supply of photons, century after century, millennium after millennium, without interruption. In reality, stars are anything but eternal. They're born, they burn, and they die. And the timescales on which they do this vary enormously. The most massive stars in the universe, the blue supergiants that outshine everything around them, are also the shortest lived. A star 50 times the mass of our own burns through its nuclear fuel with ferocious speed. Its core temperatures are so extreme and its fusion reactions so violent that it exhausts its hydrogen supply in just a few million years. A few million years. In a universe 13.8 billion years old, that is a heartbeat. These colossal stars blaze with extraordinary brightness, then detonate in supernova explosions that scatter their material across space. Their contribution to the total light of the cosmos is intense, but brief. To feel the scale of this, consider a star called a blue supergiant, roughly 60 or 80 times the mass of our own. A star like that is born inside a collapsing cloud of gas and dust, ignites its core, and begins fusing hydrogen into helium at a pace that would exhaust our star's entire fuel supply in a fraction of the time. Its surface temperature exceeds 70,000 degrees Fahrenheit. Its luminosity can be hundreds of thousands of times greater than what our own star produces. Standing at the same distance from a blue supergiant as Earth stands from our star, you would not survive for a fraction of a second. The radiation alone would be lethal beyond any measure. And yet this monster, this furnace of nearly incomprehensible power, lives for only 3 or 4 million years. That is not a rough estimate. That is the constraint imposed by nuclear physics. The more massive a star, the higher its core temperature. The higher the core temperature, the faster the fusion reactions proceed. The faster the reactions proceed, the sooner the fuel is gone. A star that shines 100,000 times brighter than ours does not live 100,000 times shorter. It lives roughly 3,000 times shorter, because the relationship between mass, luminosity, and lifespan is not linear. It is brutally steep, 3 or 4 million years. To put that in terrestrial terms, a blue supergiant born when the first ancestors of modern elephants appeared on the African plains would already be dead. It would have lived its entire life, exhausted its fuel, collapsed, and detonated in a supernova before the elephants finished evolving into their modern form. The geological formation of a single mountain range on Earth takes longer than the entire existence of the most luminous stars in the universe. These stars are spectacular, but they are sprinters. They burn everything they have and then they are gone. And when they are gone, they leave behind objects that emit no visible light at all. Neutron stars, which are detectable only through radio pulses and X-rays, or black holes, which emit nothing. The brightest stars in the universe end as the darkest objects in the universe. Their light is not eternal. It is an eruption, a flash, a brief incandescent scream followed by permanent silence. Stars like ours are more modest. A star of roughly 1 solar mass burns hydrogen in its core for approximately 10 billion years. Ours is currently about 4.5 billion years into that lifespan. It will continue for another 5 billion years or so before swelling into a red giant, shedding its outer layers, and collapsing into a white dwarf. Even the most ordinary stars have expiration dates. At the lower end of the mass scale are red dwarfs, dim and cool, burning their fuel so slowly that they can persist for trillions of years. But their light output is a fraction of what larger stars produce. A red dwarf emits so little light that even nearby examples are invisible to the naked eye. They contribute almost nothing to the brightness of the sky. What all of this means is that at any given moment, the universe does not contain an infinite number of stars burning at full brightness. It contains a finite population, each at a different stage of its life cycle. Some newly ignited, some middle-aged, some dying, some already dead. The total luminosity of the cosmos at any moment is a finite number. And that finite number, spread across the vastness of space, is nowhere near enough to light up every direction in the sky. The assumption that stars are eternal was never true. Stars are temporary objects. Their fuel runs out. They die. And when they die, their light stops. The universe is littered with the remnants of stars that once shone and no longer do. White dwarfs cooling in the dark, neutron stars spinning in silence, black holes emitting no light at all. For every star that burns tonight, there are countless others that have already gone out. The universe is not a room filled with lamps that have been on forever. It is a room where lamps are constantly flickering on and off, and most of them are off at any given time. There is a third assumption built into the paradox that also collapses under observation. The paradox imagines stars distributed uniformly through space, spread evenly in every direction at every distance, like grains of salt stirred into a vast container of water. If that were true, The mathematics of light accumulation would hold. Every shell of space would contribute equally. The brightness would build and build. But stars are not distributed uniformly. Neither are galaxies. The large-scale structure of the universe, revealed by decades of galaxy surveys and computer simulations, looks nothing like a smooth uniform field. It looks like a web. Imagine a vast three-dimensional network of filaments, threads of matter stretching across hundreds of millions of light years, intersecting at dense nodes where galaxy clusters sit. Between the filaments are voids, not small gaps, enormous empty regions, some stretching 300 million light years across, where almost no galaxies exist. These are the largest known structures in the universe, and they are defined by their emptiness. Galaxies cluster along the filaments and at the intersections. They gather in groups and clusters, bound together by gravity. Our own galaxy, the Milky Way, sits within a modest collection called the Local Group, which contains more than 80 galaxies spread across roughly 10 million light years. Beyond the Local Group, other groups and clusters line up along the filaments of the cosmic web, separated by voids so vast that light crossing them would detect almost nothing along the way. The most detailed picture of this structure came from a project called the Sloan Digital Sky Survey, which began mapping the positions of galaxies in the late 1990s and has continued in various phases ever since. By recording the locations and redshifts of millions of galaxies, the survey produced three-dimensional maps of the cosmic web that revealed its architecture in stunning detail. The maps show filaments of galaxies stretching for hundreds of millions of light years, connecting clusters at their intersections like threads in an enormous web. And between the filaments, the voids. Some of the largest known voids span 300 million light years or more. To cross one at the speed of light would take 300 million years, and during the entire crossing, you would encounter almost nothing. No galaxies, no clusters, no significant concentrations of matter. Just hydrogen gas so thin and so cold that it barely qualifies as material. The Bootes void, one of the largest individual voids ever mapped, stretches roughly 330 million light years across. It contains so few galaxies that when it was first identified in 1981, astronomers initially suspected a problem with their data. It seemed impossible that a region so vast could be so empty, but the emptiness was confirmed, and it was real. The Bootes void is not unique. It is representative. The universe is mostly void. The filaments and clusters, dazzling as they are in survey images, are the exception. The darkness between them is the rule. This is the texture of the cosmos at its largest scales. Not a uniform field of light. Not a smooth distribution of matter. A web of bright threads separated by oceans of nothing. And the dark sky reflects this architecture faithfully. Most directions you look at night point through the voids, through the gaps in the web, through regions where the universe simply did not place enough matter to produce visible light. This structure means that most lines of sight through the universe do not pass through an unbroken field of stars. They pass through voids, enormous, dark, genuinely empty regions where there is nothing to see. The light from the galaxies that do exist is concentrated along the filaments, clustered at the nodes, and absent from the yawning gaps between them. The sky has dark patches because there are dark places, real places where the matter of the universe simply is not. The universe is not a uniformly lit room. It is a sparse web of light strung across an ocean of nothing. These three facts, the finite age of the universe, the finite lifetimes of stars, and the uneven distribution of matter, together resolve the core of the paradox. The sky is dark because there has not been enough time for light from every star to reach us, because stars do not shine forever, and because the stars that do exist are clustered together with vast empty spaces between them. The assumptions behind the paradox fail on every level. The universe is not infinite in age, stars are not eternal, and matter is not spread evenly. But there is one more layer to this part of the story, and it is perhaps the most profound. Because when astronomers turned their instruments away from visible light and looked at the sky in a completely different wavelength, they discovered that the darkness we see with our eyes is an illusion. The sky is not truly dark. It is filled in every direction with a faint glow that has been traveling since the universe was barely old enough to produce light at all. In 1965, 2 radio astronomers at Bell Telephone Laboratories in New Jersey stumbled onto something they could not explain. Arno Penzias and Robert Wilson were calibrating a large horn-shaped antenna originally built for satellite communication experiments. They were picking up a persistent noise, a faint hiss of microwave radiation that seemed to come from everywhere. It did not change with the time of day. It didn't change with the seasons. It did not come from any specific object in the sky. It was uniform, omnidirectional, and constant. They checked the equipment. They removed pigeons that had been nesting inside the antenna. They cleaned and recalibrated. The noise remained. At the same time, a team of physicists at Princeton University, led by Robert Dickel, had been building a detector specifically designed to search for precisely this kind of radiation. They had predicted, based on the physics of the Big Bang, that the early universe should have produced a bath of thermal radiation that would still be detectable today, cooled and stretched by billions of years of cosmic expansion. When Penzias and Wilson learned about the Princeton group's prediction, the pieces fell into place. The story of how those pieces fell into place deserves to be told properly, because it is one of the great accidental discoveries in the history of science. Penzias and Wilson were not looking for the origin of the universe. They were radio engineers. Their antenna, a massive horn-shaped structure at Bell Telephone Laboratories in Holmdel, New Jersey, had been built for a practical purpose: communicating with the Echo satellite, one of the earliest experiments in space-based telecommunications. When the satellite project ended, Penzias and Wilson repurposed the antenna for radio astronomy. They wanted to measure the radio emissions from the Milky Way. To do that, they needed to account for every source of noise in their instrument so they could subtract it from the signal. They accounted for the noise from the antenna's electronics. They accounted for interference from nearby cities. They accounted for radiation from the atmosphere. They accounted for every known source. And when they subtracted all of it, a residual hiss remained. It was faint but persistent, corresponding to a temperature of roughly 3.5 degrees above absolute zero. It came from every direction in the sky, equally at all times of day and night, in every season. They could not explain it. They spent months trying. At one point, they discovered that pigeons had been roosting inside the horn of the antenna, leaving droppings on the reflective surface. They captured the pigeons, shipped them to a facility roughly 30 miles away, cleaned the antenna thoroughly, and tested again. The pigeons flew back. They captured them again. The noise remained. It had nothing to do with pigeons. They checked the instrument for faulty connections. They recalibrated. They tested different frequencies. The noise was always there, always the same intensity, always uniform across the sky. It behaved like no known source of interference. It behaved like something fundamental. Meanwhile, just 30 miles away at Princeton University, physicist Robert Dicker and his colleagues Jim Peebles, Peter Roll, and David Wilkinson were building their own antenna for precisely the purpose of detecting this kind of radiation. Peebles had calculated that if the Big Bang theory was correct, the universe should be filled with a residual thermal glow, cooled by billions of years of expansion to a temperature of just a few degrees above absolute zero. They were racing to detect it. When a mutual colleague connected the two groups, the realization was immediate. Penzias and Wilson had found exactly what the Princeton team was searching for. The hiss was not instrument noise, it was the afterglow of the Big Bang itself. Radiation released when the universe was less than 400,000 years old, traveling through space ever since, arriving at a horn antenna in New Jersey 13.8 billion years later, where two bewildered engineers had been trying to make it go away. Penzias and Wilson won the Nobel Prize in Physics in 1978 for the discovery. They had stumbled onto the oldest light in the universe, while trying to fix what they thought was a malfunction. The noise was not a malfunction. It was the oldest light in the universe. This radiation is called the cosmic microwave background. It was released approximately 380,000 years after the Big Bang, during an event called recombination. Before that moment, the universe was so hot and so dense that atoms could not form. Space was filled with a plasma of free protons, electrons, and photons. The photons could not travel in straight lines. Every time a photon moved, it collided with a free electron and scattered in a random direction. The universe was opaque. Imagine a fog so thick that light cannot penetrate more than a short distance in any direction. That was the state of the entire cosmos for its first 380,000 years. A wall of plasma through which no image, no signal, no photon could pass cleanly. Then the universe cooled enough for electrons to bind with protons and form neutral hydrogen atoms. The free electrons disappeared, the fog lifted, and in a cosmic instant, the photons that had been trapped in the plasma were released. They streamed outward in every direction, carrying with them a thermal imprint of the universe at that exact moment. Those photons have been traveling through space ever since. When they were first released, those photons were visible light. The universe at that moment had a temperature of roughly 5,000 degrees Fahrenheit, and the radiation had a color like the warm orange glow of a cooling ember. If you could have been there, setting aside the fact that no planets, no stars, and no solid matter existed, you would have seen a sky that glowed evenly in every direction. Not dark, not black, bright, but that was more than 13 billion years ago. Since then, the universe has expanded enormously, and the expansion has stretched those ancient photons. Their wavelengths have grown longer and longer. What was once visible light has been stretched into microwaves, invisible to the human eye and detectable only with specialized radio instruments. The temperature of the radiation today is approximately 2.7 degrees above absolute zero. It is unimaginably faint, but it is everywhere. Every cubic centimeter of space in the universe is bathed in this ancient glow. The cosmic microwave background fills the entire sky. It has no gaps. It has no dark patches. In the microwave band, the universe is uniformly bright, glowing in every direction with the afterglow of the moment the cosmos first became transparent. When Penzias and Wilson pointed their antenna at the sky and heard that faint hiss, they were hearing the birth cry of the observable universe, a sound released before any star had formed, before any galaxy existed, before anything recognizable had taken shape. The cosmic microwave background is the farthest thing we can see in any form of light. It is the back wall of the observable universe. Before it, the cosmos was opaque. No telescope, no matter how powerful, no matter what wavelength it observes in, can see beyond that wall. Everything before recombination is hidden behind a screen of plasma that scattered every photon into incoherence. The dark sky you see at night is not truly dark. Between the stars, between the galaxies, behind everything visible, there is this glow. You cannot see it because your eyes evolved to detect a narrow band of the electromagnetic spectrum that no longer carries this signal. The universe stretched the oldest light beyond the reach of biology, but instruments can detect it, and they have. The Cosmic Background Explorer satellite, launched in 1989, mapped it with precision and confirmed that its spectrum is a near-perfect thermal curve, matching the prediction of Big Bang theory to an extraordinary degree. Later missions, the Wilkinson Microwave Anisotropy Probe, and the European Space Agency's Planck satellite, mapped it in finer and finer detail, revealing tiny temperature variations imprinted on the glow that correspond to the seeds of every galaxy, every cluster, every filament in the cosmic web. The cosmic microwave background is the oldest photograph of the universe has taken of itself. It shows us the cosmos as it was 380,000 years after the beginning. A hot, smooth, nearly uniform bath of radiation with faint ripples that would eventually grow into everything we see. Those ripples are the earlier structures. They are the fingerprints of gravity, acting on tiny density variations in the infant universe, pulling matter together in some places and leaving voids in others. The web of galaxies that exist today began as whispers in the microwave glow. This is what the darkness of the night sky hides. Not emptiness, not nothing. A wall of light so ancient and so stretched that human eyes cannot detect it, but instruments can. Behind the stars, behind the galaxies, behind the most distant object any telescope has ever resolved, the cosmic microwave background sits like a curtain drawn across the stage of cosmic history. Everything before it is hidden. Everything after it is what we call the visible universe. And the visible universe, vast as it is, represents only the part of the story that light has had time and ability to carry to us. The finite age of the cosmos, the finite lifetimes of stars, the uneven distribution of matter, and the existence of the cosmic microwave background together provide a nearly complete explanation for why the night sky is dark. Poe's intuition was correct. The universe has not existed long enough for every line of sight to be filled with starlight. Kelvin's thermodynamic objection to dust was correct. Interstellar material cannot hide the light without eventually re-radiating it. The paradox is resolved. The darkness is explained. Nearly. Because there is one more force acting on the light of the cosmos, and it does something that finite age alone cannot do. The finite age of the universe limits how far light has traveled. But this other force changes the light itself. It takes photons that are already in transit, photons that have been crossing space for billions of years, and it alters them. It stretches their wavelengths. It drains their energy. It moves them, step by step, out of the visible spectrum and into wavelengths that no biological eye in the history of life on Earth has ever been equipped to detect. The cosmic microwave background is the proof. That ancient light was once visible. It is not visible anymore. Something did that. Something took the oldest light in the universe and pushed it beyond the edge of perception. That something is not a filter. It is not dust. It is not absorption. It is the expansion of space itself. And when you understand what expansion does, not just to the microwave background, but to every photon from every galaxy across the entire observable universe, the darkness of the night sky stops being a puzzle and starts becoming something far more disturbing. The universe is not just dark because of what has not yet reached us. It is dark because something is actively changing the light that is on its way, stretching it, weakening it, and in many cases, moving it permanently beyond the boundary of what we will ever be able to see. That transformation is happening right now to every photon in the cosmos, and it is accelerating. In 1912, an astronomer named Vesto Slipher pointed a telescope at a faint smudge of light in the constellation Andromeda, and did something no one had done before. He measured the spectrum of that smudge, the individual wavelengths of light it emitted, and compared them to the wavelengths produced by the same chemical elements in laboratories on Earth. What he found was strange. The wavelengths did not match. They were shifted. In this particular case, the light was displaced toward the blue end of the spectrum, meaning the object was approaching us. The result was curious, but it was a single measurement. There was no way to know yet what it meant. Over the next several years, Slipher measured the spectra of dozens of similar objects, and a pattern emerged that dwarfed that first observation. The overwhelming majority were shifted in the opposite direction, toward the red, away from us, longer wavelengths, lower energy. Something was happening to the light between there and here, and whatever it was happening consistently, across object after object, in nearly every direction Slipher looked. At the time, nobody knew what these faint smudges actually were. Many astronomers believed they were clouds of gas within the Milky Way. But Slipher's redshift measurements were the first hint of something far larger and far stranger. The light from these objects was being altered during its journey across space, and the pattern of that alteration would eventually reveal the single most important fact about the universe that humans have ever discovered. The universe is not still, it is expanding. The full picture came together in the late 1920s through the combined work of several people. Henrietta Leavitt had developed a method for measuring cosmic distances using a specific type of pulsating star. Edwin Hubble, working at the Mount Wilson Observatory in California, used Leavitt's method to show that the faint smudges Slipher had studied were not gas clouds within the Milky Way. They were entire galaxies, vast island systems of stars lying millions of light years beyond our own. The universe was suddenly unimaginably larger than anyone had believed. Then Hubble took the next step. But Hubble could not have taken that step without the work of a woman whose contribution was, for decades, almost entirely overlooked. Henrietta Swan Leavitt was a human computer at the Harvard College Observatory. In the early 1900s, women were not permitted to operate the telescopes. They were hired to examine photographic plates, catalogue stellar brightness, and perform calculations that the senior astronomers considered tedious. Leavitt did this work with extraordinary precision. She studied a class of stars called Cepheid variables, stars whose brightness rises and falls in a regular rhythm, pulsing like a slow heartbeat over periods of days or weeks. While examining Cepheids in the small Magellanic Cloud, a satellite galaxy of the Milky Way, Leavitt made a discovery that would reshape the entire science of cosmology. She found a tight relationship between a Cepheid's pulsation period and its intrinsic luminosity. The longer the period, the brighter the star. This meant that by measuring how fast a Cepheid pulsed, you could calculate how bright it truly was. And by comparing that true brightness to how bright it appeared from Earth, you could calculate how far away it was. Leavitt had handed astronomy a cosmic ruler. For the first time, distances to objects far beyond the reach of simple parallax measurements could be determined. Without this tool, Hubble could not have measured the distances to the faint smudges Slipher had studied. Without this tool, no one could have proved that those smudges were galaxies. Leavitt died in 1921, before the full impact of her work became apparent. She never received the Nobel Prize. In 1924, a Swedish mathematician attempted to nominate her, only to learn that she had already died. The nomination was never submitted. The Nobel is not awarded posthumously. Hubble used Leavitt's Cepheid method at the Mount Wilson Observatory in California, working with the 100-inch Hooker telescope, the most powerful instrument in the world at the time. He identified Cepheid variables in several of the nebulae Slipher had measured and calculated their distances. The numbers were staggering. These objects were not gas clouds within the Milky Way. They were millions of light years away. They were entire galaxies. Then he combined his distance measurements with Slipher's redshift data and discovered a pattern so clean, so consistent that it could not be coincidence. The farther away a galaxy was, the more its light was redshifted. The relationship was linear. Double the distance and you double the redshift. Triple the distance, triple the shift. Every galaxy in the observable universe appeared to be moving away from us, and the ones farther away were receding faster. Hubble had found the expansion of the universe. Around the same time, the Belgian physicist Georges Lemaitre had independently derived the same conclusion from Einstein's equations of general relativity. Lemaitre proposed that if the universe is expanding now, then it must have been smaller in the past. Trace the expansion backward in time and everything converges toward a single point of extraordinary density and temperature. This was the seed of what would become the Big Bang Theory. But the expansion is not what most people imagine when they first hear about it. It is not an explosion. It is not galaxies flying outward through space like shrapnel from a bomb. It is something far more unsettling than that. Space itself is expanding. The fabric of the cosmos, the medium through which light travels, the stage on which galaxies sit, is stretching. Not at the edges, not in one direction. Everywhere, uniformly, all at once. Every point in space is moving away from every other point. The galaxies are not racing through a static void. They are sitting relatively still while the void itself grows. Here is a way to picture this that is not perfect, but captures the essential idea. Imagine the surface of a balloon, and imagine that surface is all there is. There is no inside, no outside, only the surface. Now draw dots on that surface with a marker. Each dot is a galaxy. As the balloon inflates, every dot moves away from every other dot. No dot is at the center, no dot is at the edge. The expansion is happening everywhere on the surface simultaneously. The dots are not moving across the surface. The surface is stretching between them. Now imagine a tiny ant walking from one dot to another. The ant moves at a fixed speed. If the dots are close together, the ant crosses the gap easily. But if the balloon keeps inflating while the ant walks, the gap grows as the ant crosses it. The ant might still arrive, but it takes longer than expected because new surface appeared during the journey. And if the balloon inflates fast enough, the gap between two distant dots might grow faster than the ant can walk. The ant would walk forever and never arrive. The distance would grow faster than the ant could close it. Light is the ant. Space is the balloon. And some galaxies are already so far away that the space between us is stretching faster than light can cross it. This is what redshift actually is. It is not caused by galaxies moving through space away from us, at least not primarily. It is caused by space itself expanding while the light travels through it. When a photon leaves a distant galaxy and begins its journey toward us, it has a specific wavelength. As that photon crosses space, the space it is crossing stretches. The photon stretches with it. Its wavelength gets longer. Longer wavelengths mean lower energy, and for visible light, a shift toward the red end of the spectrum. The farther the light has traveled, the more space it has crossed, the more stretching has occurred, and the greater the redshift. This is not a subtle effect. For nearby galaxies, the redshift is small, a slight warming of the colour. For galaxies billions of light years away, the redshift is dramatic. Light that was emitted as ultraviolet arrives as infrared. Light that was emitted as visible blue arrives as radio waves. The photons are the same photons. They left their source with a specific wavelength and energy, but the universe stretched them during the journey, draining their energy, pushing their wavelengths longer and longer until they arrive at our instruments fundamentally altered. Follow a single photon to see what this means in practice. A star in a distant galaxy, 8 billion light years away, emits a photon of blue light. At the moment of emission, the photon has a wavelength of roughly 450 nanometers. It is vivid blue. It carries a specific amount of energy determined by that wavelength. It leaves the star and enters the intergalactic void, traveling at 186,000 miles per second, crossing space in a perfectly straight line. For the first billion years of its journey, space expands modestly. The photon's wavelength stretches slightly. Blue becomes a cooler blue, then shifts toward green. The photon has lost a small fraction of its energy. It is still visible light. A human eye could still see it, though the color would be wrong. After 3 billion years, the stretching has moved the photon into the yellow range, then orange. The photon is now noticeably different from the blue light that left the star. It carries less energy. Its wavelength is longer. The universe has been gently pulling it apart for 3 billion years. After 5 billion years, the photon crosses into red. It is near the edge of what human vision can detect. The long wavelength limit of the human eye is roughly 700 nanometers. The photon is approaching that boundary. A little more stretching and it will cross over into infrared, invisible to any biological eye that has ever existed on Earth. After 6 billion years, it crosses. The photon is now infrared. It still exists. It is still traveling at the same speed, but it is no longer light in any way that a human being would recognize. It has become heat radiation, detectable only by instruments designed to sense wavelengths that the eye cannot. By the time the photon completes its 8 billion year journey and arrives at a telescope orbiting Earth, its wavelength has roughly doubled from where it started. The blue light is now near infrared. The photon carries half the energy it had when it was emitted. The universe took that energy, not by absorbing it, not by blocking it, but by stretching the space the photon traveled through, which stretched the photon itself. Half the energy that star put into that single photon was lost to the expansion of the cosmos. Not destroyed, redistributed into the stretching of space-time. Gone from the photon, absorbed by the universe at large. Irrecoverable. Multiply that single photon by every photon from every star in every distant galaxy, and you begin to see why the sky is dark even though the universe is full of stars. The light is there, but the universe has been rewriting it during the journey, draining its energy, pushing it past the threshold of biological detection, rendering it invisible one wavelength at a time. The cosmic microwave background is the most extreme example of this stretching. That ancient radiation, the afterglow of the Big Bang, has been traveling through expanding space for more than 13 billion years. Over that time, the universe has expanded by a factor of roughly 1,100. Every wavelength in that primordial light has been multiplied by the same factor. Photons that once carried the energy of visible light now carry the energy of faint microwaves, detectable only by instruments cooled to near absolute zero. The entire sky glows with this ancient light, but the universe stretched it so far beyond the visible spectrum that no eye, no biological detector, no organism that has ever lived could perceive it without technology. The darkness of the night sky is partly an illusion created by expansion. The sky is not truly dark. It is full of light that has been pushed beyond perception. But the stretching of light is not the most disturbing consequence of expansion. The most disturbing consequence is what expansion does to the reach of information itself. Because the universe is expanding, and because that expansion is accelerating, there are regions of the cosmos that are permanently beyond our ability to observe or contact. These regions are separated from us by a boundary called the cosmic event horizon. It is not a physical surface. It is not a wall. It is the distance beyond which the expansion of space outpaces the speed of light. Beyond that boundary, a photon emitted today, aimed directly at us, will never arrive. The space between us and that photon will grow faster than the photon can cross it. The light will travel forever and never reach us. This is not a violation of the speed of light. Nothing is moving through space faster than light. Space itself is expanding, and the accumulated expansion over sufficiently large distances produces a recession rate that exceeds light speed. The galaxy is not zooming away from us like a spaceship. It is sitting still while the distance between us grows faster than light can compensate. The cosmic event horizon currently sits at roughly 17 billion light years from us. Every galaxy beyond that distance is, in terms of new light emitted today, permanently cut off. Their photons will never arrive. They are beyond the reach of any signal, any probe, any message, any technology that travels at or below the speed of light. They are gone. Not destroyed, not absent. Separated from us by the expansion of reality itself. Now here is the part that should unsettle you. Within that observable sphere, that bubble of everything light has had time to show us, there are roughly 2 trillion galaxies. The vast majority of them are already beyond the cosmic event horizon. Approximately 94% of them are already there, beyond the boundary where new light can reach us. They are visible to us now only because their ancient light, emitted billions of years ago, left them at a time when they were closer and the expansion was slower. That light has been traveling since before the expansion accelerated to its current pace. We see those galaxies as they were, not as they are. Where they are now and what they are doing now is permanently unknowable. We will never receive new information from them. Think about what this means in terms of what has already been lost. There are galaxies in the deep field images taken by the Hubble Space Telescope and the James Webb Space Telescope that appear as faint smudges of light. Their photons stretched and weakened by billions of years of expansion. Those images show the galaxies as they existed in the distant past when their light first left them. At that time, they were close enough and the expansion was slow enough that their photons could begin the journey and eventually arrive. But the galaxies themselves have been moving away from us the entire time the light was in transit. Their present-day positions are billions of light years farther than where the light originated. Many of those galaxies crossed the cosmic event horizon while their ancient light was still traveling toward us. The photons we see tonight were released before the expansion became fast enough to cut them off. They are messages from a sender who has since moved permanently out of range. We received the letter, but the return address no longer exists in any reachable sense. We cannot send a reply. We cannot visit. We cannot even confirm that the galaxy still exists, because no new information from it will ever arrive. Every deep field image is a gallery of farewells. Each faint dot is a galaxy whose present-day self is already unreachable. We are looking at the last light that will ever arrive from objects that are still out there, still burning, still real, but separated from us by a gap that grows wider every second, and that no technology, no matter how advanced, will ever close. The universe showed us those galaxies once. It will not show them to us again. Let that settle for a moment. 94% of the galaxies we can see are already unreachable. Their present-day reality is forever hidden. The images we have of them are fossil records, preserved in photons that started their journey billions of years before the expansion became fast enough to cut them off. We are looking at ghosts, real objects, yes, but objects whose current state is separated from us by a gap that light itself cannot bridge, and this gap is growing. Dark energy, the mysterious force driving the acceleration of cosmic expansion, has been the dominant component of the universe's energy budget for the past 5 billion years or so. Its effect is cumulative. As space expands, more space is created, and that new space carries its own dark energy, which drives further expansion. The acceleration feeds itself. The discovery that the expansion is accelerating was itself a shock. For most of the 20th century, cosmologists assumed that the expansion was slowing down. That made intuitive sense. The universe is full of matter, and matter has gravity, and gravity pulls things together. The mutual gravitational attraction of every galaxy on every other galaxy should have been acting as a brake on the expansion, gradually decelerating it over billions of years. The question was not whether the expansion was slowing. The question was whether it was slowing fast enough to eventually stop and reverse, pulling everything back together in a final collapse, or whether it would simply coast outward forever, decelerating but never quite stopping. In 1998, two independent teams of astronomers set out to measure the deceleration rate using a specific type of stellar explosion called a Type 1a supernova. These explosions have a nearly uniform intrinsic brightness, which makes them excellent distance markers. By comparing how bright a Type 1a supernova appeared in telescope images to how bright it actually was, researchers could calculate how far away it was. and by measuring the redshift of its host galaxy, they could determine how fast it was receding. Combining the two measurements across dozens of supernovae at different distances would reveal whether the expansion was slowing as expected. Both teams found the opposite. The distant supernovae were fainter than they should have been, not by a small amount, by a significant, consistent margin. The galaxies hosting those explosions were farther away than a decelerating universe would predict. The expansion was not slowing down, it was speeding up. The result was so unexpected that both teams spent months rechecking their data, searching for errors, looking for alternative explanations. They found none. The acceleration was real. Something was pushing the universe apart, overcoming the gravitational pull of all the matter in the cosmos. And it was getting stronger as the universe aged. Physicists named this unknown force dark energy, a label that reflects how little we understand about it. We know it exists. We know it dominates the energy budget of the universe, comprising roughly 68% of the total. We know its effect is accelerating. We do not know what it is. The cosmic event horizon does not shrink. It creeps inward. Over time, galaxies that are currently within our observable range will cross the horizon and disappear. Not in a flash. Not with a signal. They will simply grow fainter and redder, their light stretching further and further toward longer wavelengths, until the photons reaching us carry so little energy that they become undetectable. The galaxy fades from view and vanishes, not because it has been destroyed, but because the universe has carried it beyond the reach of light. Consider what this means for the most distant object humanity has ever observed. The galaxy designated MOMZ-14 was confirmed in 2025 as the most distant galaxy ever spectroscopically verified. Its light has been traveling for more than 13 billion years. We see it as it existed just 280 million years after the Big Bang, when the universe was barely 2% of its current age. Its redshift is 14.44, meaning the light from this galaxy has been stretched by a factor of more than 15 since it was emitted. When that light left a MOMZ-14, the galaxy was relatively close, a few billion light years away. But the universe has been expanding throughout the entire journey of those photons. Today, accounting for all the expansion that has occurred since the light was emitted, MOMZ-14 is approximately 34 billion light years from us. The light we see is ancient. The galaxy is already far beyond the cosmic event horizon. Nothing it emits today will ever reach us. Every observation we make of it is a farewell we did not know we were witnessing. The James Webb Space Telescope, launched in late 2021, was designed in part to push the observable frontier as close to the cosmic microwave background as instruments allow. Its infrared sensors can detect light that has been redshifted far beyond the visible spectrum, revealing galaxies from the first few 100 million years of cosmic history. It is showing us objects whose light has been traveling for nearly the entire age of the universe. But even Webb has limits. Beyond a certain redshift, the light is stretched so thin, so faint, so far into longer wavelengths that even the most sensitive instruments cannot recover it. There is a practical horizon beyond the theoretical one, and Webb is pressing against it. What lies beyond the farthest galaxy Webb can see is not darkness in the way we normally use the word. It is the cosmic microwave background, that ancient glow from 380,000 years after the Big Bang. And behind the microwave background is the opaque wall of plasma from the universe's first era. And behind that wall is the Big Bang itself, the event from which all light, all matter, all space, and all time emerged. All of it is in the darkness. Every chapter of cosmic history, from the local void between neighboring stars to the primordial fire that burned before the first atom formed. The dark sky is carrying all of it, encoded in wavelengths we cannot see, in absences we have not yet learned to decode, in distances that dwarf every measurement humanity has ever attempted. And the darkness is not finished with us. It has more to say than we have so far understood, and the stack is getting taller. Because the expansion of space is accelerating, the future sky will be darker than the sky we see today. Not in our lifetimes. Not in the lifetime of our species. Probably. But on cosmic timescales, the change is relentless. Over the next 100 billion years or so, every galaxy that is not gravitationally bound to our own local group will be carried beyond the cosmic event horizon. Their light will redshift toward infinity. Their images will fade from the sky. Eventually, a future observer in the merged remnant of the Milky Way and Andromeda will look out at a sky that contains only their own galaxy, surrounded by perfect blackness. No other galaxies will be visible, not because they were destroyed, because they were carried away. The timeline for this isolation is long by human standards, but not by cosmic ones. The Milky Way and Andromeda are currently approaching each other at roughly 250,000 miles per hour, pulled together by their mutual gravity. In roughly 4 to 5 billion years, the two galaxies will collide and merge into a single, enormous, elliptical galaxy that astronomers have informally named Milkdromeda. The other members of the local group, dozens of smaller galaxies bound to us by gravity, will eventually be absorbed into this merged system as well. While this merger unfolds, the rest of the universe continues to expand. Galaxies beyond the local group will recede faster and faster. The nearest large galaxy clusters, currently tens of millions of light years away, will be carried past the event horizon over the next tens of billions of years. One by one, the clusters that populate the observable sky today will fade, their light growing redder and dimmer with each passing epoch, until the last photons from the last external galaxy arrive carrying so little energy that no instrument could distinguish them from the quantum noise of empty space. The cosmic microwave background, which currently fills the sky at a temperature of 2.7 degrees above absolute zero, will be stretched further as well. Its wavelength will grow longer, its temperature will drop. Over hundreds of billions of years, it will be pushed to wavelengths so extreme and energies so low that detecting it would require instruments of a sensitivity that may be physically impossible to build. The afterglow of the Big Bang, the most important cosmological signal ever discovered, will be stretched to silence. What remains is a single galaxy, Milkdromeda, surrounded by blackness. The stars within it will continue to burn for a time, but star formation will eventually slow as the galaxy exhausts its supply of cold gas. The last stars to form will be small red dwarfs, burning their fuel with miserly efficiency, glowing for trillions of years before fading to black. And when the last red dwarf goes out, the galaxy will become a graveyard of white dwarfs, neutron stars, and black holes, drifting in total darkness with no light arriving from anywhere. That is the future the expansion of space is building, not in theory, in measured trajectory, The acceleration is confirmed. The dark energy is real. The horizon is tightening. And the sky, already dark, is on a path toward a darkness so complete that the universe will have erased every visible trace of its own history. And here is the part that should disturb you most. The astronomers of that era, if they exist, will not know any of this happened. They will study their single galaxy. They will measure its stars and its chemistry and its structure. They will build a cosmology based on what they can see. And that cosmology will be wrong. It will describe a lone galaxy in an infinite static void, and there will be no way to know it is wrong, because every contradicting fact will be beyond the horizon forever. The records of the cosmos are being erased by the cosmos itself. Not quickly, not violently. Slowly, patiently, one galaxy at a time, as expansion carries the evidence past the point of no return. This is what the dark sky is doing right now. It is not static. It is not fixed. The darkness is growing. The horizons are tightening. Every moment that passes, space expands a little more, light stretches a little further, and the universe becomes a little less visible to anyone standing inside it. The dark patches between the stars are not permanent features of an unchanging landscape. They are the leading edge of a process that will eventually consume the entire observable sky. The universe is not hiding its light behind dust. It is not too young to have filled every sight line with stars. Those are pieces of the answer, but they are not the whole answer. The deepest reason the sky is dark is that the universe is actively working against the light. Expansion stretches photons. Acceleration pushes galaxies beyond reach. The structure of space-time itself ensures that most of the light that has ever been emitted will never be seen by any observer, anywhere. The darkness is not passive. It is a process. It has a direction, and that direction is toward more darkness, not less. When you understand this, the night sky stops looking like an absence. It starts looking like a message. Every dark patch is telling you something specific. It is telling you about time, about distance, about the speed of light, about the expansion of space, about the finite lives of stars, about the structure of matter, about horizons that exist everywhere for every observer, and about a future in which the sky grows darker and darker until the evidence of the wider universe is gone. The darkness is doing something. It is not passive. It is not simply the absence of light that has not yet arrived. It is actively being shaped, deepened, expanded by the same forces that built the universe itself. And what that darkness actually contains, what it is trying to show us, may be the most unsettling part of this entire story. Look at the night sky one more time. Not casually. Not the way you look at it when you step outside to check the weather or walk the dog. Look at it the way you would look at a document you have just been told contains a message. Because it does. Every piece of darkness you see between the stars is information. Not emptiness, not absence, not the void that ancient philosophers imagined when they pictured a cosmos trailing off into nothingness. Each dark patch is a sentence written in physics, and every sentence says something specific about the universe you live in. The blackness is a record, and now that you understand what causes it, you can begin to learn more about it. Start with the nearest layer. The dark sky immediately around the visible stars is simply empty local space. The stars you see with your naked eye are almost all within a few thousand light years, a tiny neighborhood inside a galaxy that stretches more than 100,000 light years across. Between those nearby stars, there is gas, there is dust, there are planets and debris and the remnants of stellar explosions. but not enough luminous material to fill the gaps. This layer of darkness is the most straightforward. It is the space between things. But step beyond the local neighborhood and the darkness changes character. The next layer out contains galaxies, billions of them. Galaxies whose light is real, whose stars are burning right now, but whose combined glow is too faint, too diffuse, too spread across the sky for the human eye to resolve. If your eyes were 1,000 times more sensitive, the sky would not look black. It would shimmer with a faint haze of galactic light, a gossamer veil of photons arriving from millions and billions of light years away. This layer of darkness is not empty at all. It is full of light that is simply too weak for your biology to register. Beyond that lies a deeper layer. Here the galaxies are so distant that their light has been traveling for billions of years. During that journey, the expansion of space has stretched their photons, shifting them out of the visible spectrum entirely. These galaxies are not faint. They're invisible, at least in visible light. Their photons have been redshifted into infrared, into microwave, into wavelengths that no biological eye on Earth has ever been equipped to perceive. Telescopes working in infrared can see them. The James Webb Space Telescope has revealed thousands of them, glowing in wavelengths that would be completely dark to any human standing under the open sky. This layer of darkness is not absence. It is concealment by physics, light made invisible by the very structure of space-time. Go deeper still and you reach the cosmic microwave background, that ancient afterglow that fills every direction without gap or interruption. It is always there, saturating every direction without exception. But in this context, it means something different. It is not just a discovery. It is a layer of the darkness. Your eyes pass through it every time you look at the sky and register nothing. The ancient glow washes over your retina, carrying the imprint of the infant universe, and your biology does not even notice. You look right through the oldest light that exists and see only black. That is how completely expansion has disguised it. And behind the cosmic microwave background lies the final layer. Not darkness caused by distance or expansion, but something older. The plasma wall from the universe's first era. The opaque barrier that has existed since the beginning. Everything that happened in those earliest moments is locked behind it permanently. No telescope operating at any wavelength will ever see through it. The universe began in a cage of light, and the bars have never opened. This is not darkness caused by distance or expansion. It is darkness caused by the physical state of the universe itself. The early cosmos was a cage for light, and the bars of that cage have left a permanent shadow on our ability to see backward in time. The night sky, when you understand it this way, is not one kind of dark. It is 5 kinds of dark, stacked on top of each other, each one caused by a different physical fact, each one hiding a different piece of the universe. Local emptiness, distant faintness, red-shifted invisibility, the microwave afterglow, and the opaque wall of the primordial plasma. 5 layers, 5 reasons, 5 kinds of information, all encoded in the blackness between the stars. This is what the darkness is. It is not nothing. It is a composite portrait of every limit the universe places on the act of seeing. When you look at a dark patch of sky, you're not staring into a void. You're staring at the edge of what physics allows you to perceive. The darkness is the boundary, and the boundary is real. Now here's the part that most discussions of this topic leave out. The part that, once you understand it, changes the way the dark sky feels. The darkness is evidence. Specific, testable, physical evidence, and it is evidence of something that most people have never considered. The universe has a beginning. That sentence sounds simple. You have probably heard it before. The Big Bang happened approximately 13.8 billion years ago. Fine. But the dark sky is not just consistent with that fact. It is caused by that fact. The darkness you see tonight is a direct, visible, immediate consequence of living in a universe that has not existed forever. If the universe were eternal, the sky would not be dark. That was the whole point of the paradox. An infinite, static, eternal universe filled with stars produces a sky as bright as the surface of a star. Every line of sight terminates at a stellar surface. The total energy is unbounded. The darkness would be impossible. The fact that you can step outside tonight and see blackness between the stars means the universe is not eternal. Not in theory, not as a mathematical deduction, as a sensory experience. Your eyes are detecting the finite age of the cosmos every time you look up. The darkness is the evidence, arriving at your retina in real time, carried by the absence of photons that would be present if the universe had no beginning. This is what Olbers' paradox truly revealed. Not a puzzle about stars and dust and distances. A clue. One of the most powerful clues in the history of science. The dark night sky is observational evidence for the Big Bang. Not supplementary evidence, not a footnote. One of the original, foundational reasons that physicists in the 20th century accepted that the universe had a beginning. The darkness came first. The theory followed, and the darkness is evidence of more than a beginning. It is evidence of expansion. Every photon that has been redshifted out of visibility is a data point. Every galaxy whose light arrives, stretched and weakened, is a measurement. The redshift of the cosmic microwave background, from visible light to microwaves, a stretching factor of more than 1,000, is a direct record of how much the universe has expanded since it became transparent. The dark sky is not just showing you that the universe began, it is showing you that the universe has been growing ever since, and it is showing you approximately how much. The darkness is evidence of horizons, the existence of a cosmic event horizon, a boundary beyond which new light can never reach us, is encoded in the sky. Every direction you look that does not terminate at a visible galaxy might be pointing toward a galaxy that is beyond the horizon. Its light, emitted right now, will never arrive. The darkness in the direction is not temporary. It is permanent. It is the visible signature of a limit built into the geometry of expanding space-time. The universe is structured in a way that guarantees certain regions are forever hidden, and the dark sky is where that guarantee becomes visible. And the darkness is evidence of the finite lives of stars. Every stellar remnant that no longer shines, every white dwarf cooling in silence, every neutron star too faint to detect, every black hole emitting nothing at all, represents a contribution to the darkness. Stars that once burned have gone out. Their light has passed and will not return. The darkness contains the memory of their absence. It is the shadow cast by mortality on a cosmic scale. Every one of these facts, the beginning, the expansion, the horizons, the mortality of stars, is written in the blackness. The dark sky is the most information-dense object in your nightly experience, and almost no one reads it. There is something deeply unsettling about realizing this, and it is worth sitting with the discomfort, rather than rushing past it. We are used to thinking of darkness as the default, Light is the exception. Stars are the special objects. The glow is what demands explanation. The darkness is just the background, the nothing in which the something sits. That is exactly backward. In a universe that obeyed the old assumptions, infinite, eternal, static, uniformly filled with stars, light would be the default. The entire sky would glow. Darkness would be the anomaly. The fact that we live in a universe where darkness dominates, where blackness fills the overwhelming majority of the visible sky, is the anomaly. The darkness is what needs explaining. The darkness is what contains the information. The darkness is the surprise. And the information it contains is not comfortable. It tells us that we live in a universe with limits. Limits on age, limits on visibility, limits on reach, limits that are not imposed by our technology or our intelligence, but by the structure of space-time itself. No civilization, no matter how advanced, no matter how powerful, no matter how long-lived, can see beyond the cosmic event horizon. No telescope, built at any point in the future of the universe, can detect photons that were stretched to zero energy by infinite expansion. No instrument can peer through the opaque wall of the primordial plasma. These are not engineering challenges. They are physical laws. The universe does not allow certain information to travel, and the dark sky is where that prohibition becomes visible. This is what makes the darkness horrifying, if you're willing to use that word honestly. It is not horror in the way of monsters or disasters. It is horror in the way of realizing that the room you live in has walls you cannot see. And those walls are closing in, slowly, imperceptibly, but with absolute certainty. The observable universe is not shrinking in the sense that it is getting smaller today, but it is losing content. Galaxies are being carried beyond the event horizon. Information is being permanently removed. The future sky will contain less evidence of the wider universe than the sky we see tonight. And the sky we see tonight contains less than the sky that existed 1 billion years ago. The universe is erasing its own history, not with violence, with distance, with expansion, with time. That future isolation, in which expansion erases all external evidence, is already underway. But it is not only the future that is hidden. Consider the present moment. Right now, stars are burning in galaxies so far away that their light, emitted at this instant, will never arrive. Not in 1 billion years, not ever. Those stars are real. Their photons are being released right now, and every one of those photons will be stretched into meaninglessness by the expansion of space before it crosses the distance between us. The overwhelming majority of stars that exist in the universe at this moment are permanently invisible to us. Their signal has already been cancelled by the geometry of space-time. Consider the arithmetic. There are roughly 2 trillion galaxies in the observable universe. Each one contains billions of stars. That gives a total somewhere in the range of 200 billion trillion stars whose ancient light has reached us in some form. But the observable universe is almost certainly a fraction of the whole. The full universe beyond our horizon may contain 10 times as many galaxies, or 100 times or more. Every star in every one of those unseen galaxies is burning right now, radiating light that will never cross the distance between us. The number of stars permanently hidden from us may dwarf the number we can see the way an ocean dwarfs a puddle. The darkness in their direction is not a delay. It is a verdict. And there is no appeal. No future technology will change this. No faster telescope, no more sensitive detector will allow us to reach across the event horizon and recover what the universe has placed beyond it. The limit is not in our instruments, it is in the structure of reality. We are lucky. That word does not appear often in scientific contexts, but it belongs here. We exist at a moment in cosmic history when the evidence is still visible. The cosmic microwave background is still detectable. Distant galaxies are still within view, even if their present-day selves are already beyond reach. The expansion is measurable. The redshifts are recordable. The entire story of the universe, its beginning, its expansion, its structure, its horizons, is written in the sky, available to anyone with the right instruments and the willingness to look. That window will not last forever. The evidence is leaving. The sky is getting darker, and the information it carries is being diluted, stretched, pushed past the point of recovery. We are not at the beginning of our ability to read the cosmos. We are closer to the middle, and eventually the book will close. This is the deepest meaning of the dark night sky. It is not showing us nothing. It is showing us everything the universe is willing to reveal, and it is showing us the boundary where that willingness ends. The dark patches are the margins of the page, the places where the story stops, not because the story is over, but because the rest of it is out of reach. When you look at the night sky, you are not seeing an empty universe. You are seeing a full universe with limits. A universe that had a beginning and carries the scars of that beginning in the glow of the microwave background. A universe that is expanding and encodes that expansion in the reddened, stretched, weakened light of distant galaxies. A universe that has horizons and enforces them with the geometry of space-time itself. A universe where stars are born and die and leave behind silence. A universe where matter clusters along filaments and leaves voids so enormous that light crossing them would find nothing at all. All of that is in the darkness. All of it. Every time you look up. The paradox that began this story asked a simple question. If the universe is full of stars, why is the sky dark? The answer, assembled across centuries by Kepler, Halley, Olbers, Poe, Kelvin, Hubble, Penzias, Wilson, and hundreds of physicists working across the 20th and 21st centuries, is this. The sky is dark because the universe is not infinite in age, because light travels at a finite speed and has not had time to arrive from every direction, because stars are born and die, and at any given moment the total luminosity of the cosmos is finite, because matter is not spread evenly, but clustered along filaments separated by enormous voids, because the expansion of space stretches light, draining its energy, shifting it out of the visible spectrum, rendering it invisible to any biological eye, because that expansion is accelerating, creating horizons beyond which no new light can ever reach us, because the early universe was opaque, and the light from its first 380,000 years is sealed behind a wall of plasma that no instrument can penetrate. The sky is dark because the universe has a history, and that history places limits on what can be seen from any single point within it. And the most disturbing part is this. The darkness is not a flaw in the universe. It is not a gap in the data. It is not a problem to be solved. The darkness is the correct appearance of a universe that is finite in age, expanding in scale, and structured in a way that guarantees most of its content is hidden from any observer, anywhere, at any time. The dark sky is what a universe with these properties looks like from the inside. There is no other way it could look. The darkness is not wrong, it is precise. It is exactly what the physics predicts. When we look into the dark, we are not seeing nothing. We are seeing the limits of what the universe allows us to see. And those limits are not arbitrary. They are the deepest truths the cosmos has to offer. The age of the universe, the speed of light, the expansion of space, the mortality of stars, the existence of horizons. Every one of these facts is a fundamental property of reality, and every one of them contributes to the darkness overhead. The night sky is not empty. It is the most honest thing the universe has ever shown us. It does not lie. It does not exaggerate. It does not hide behind complexity. It simply shows you what a universe with a beginning, an expansion, and a set of unbreakable physical laws looks like when you stand inside it and open your eyes. The answer to the question we start with, why is the universe dark, is not that something is missing. It is that something is there. Structure is there. History is there. Limits are there. The darkness is not the absence of a story. It is the story, told in the only language the universe uses, which is the language of light, and the silence where light cannot reach. The sky was dark last night. It will be dark tonight. And it will be dark every night for as long as there are eyes to see it, and minds to wonder why. And every night, it will be telling the same story. A universe that began. A universe that is expanding. A universe that has edges it will not let you see past. A universe that is slowly, quietly, irreversibly carrying its own evidence beyond the reach of anyone who might read it. That is what the darkness means. That is why it is there. And once you know it, you will never look at the night sky the same way again. The dark is not empty. The dark is full. And the fullness of the dark is the most important thing the universe has ever tried to tell us.